Continuing our discussion of thermodynamics, we now turn to the concept of heat. Heat, represented by a capital Q, typically in physics textbooks, is the energy transferred between a system and its environment because of a temperature difference that exists between the two. So if you put two objects together that are a different temperature, heat will flow from the hotter object to the cooler object until thermal equilibrium is achieved, i.e. they're the same temperature. You could see this by dropping an ice cube in a pot of water, right? Depending on the temperature of the water, ice will melt, right? The object will be increase in temperature, will probably melt. The rest of the liquid will decrease in temperature. That's why you add ice cubes to a drink that isn't very cold, to make it cold. Heat transfers from hot objects to cool objects, never the other way around. If you place, for example, let's look at general here, an environment versus a system. The environment, let's say, is your kitchen. And the system we place in that environment is a hot cup of coffee. That hot cup of coffee is at a higher temperature than the rest of the kitchen. So what ends up happening is heat transfers from the hot cup of coffee to the kitchen, to the countertop. The counter that the coffee is sitting on might feel a bit warmer. The air around the coffee cup will start to increase in temperature. And that heat comes from the coffee itself. That energy comes from the coffee itself, which drops in temperature. Given enough time, let's say you leave the hot cup of coffee on the counter overnight, when you come back the next day, the coffee is cold, we say. Where really the coffee is room temperature. It's the same temperature as the rest of the kitchen. Now, in the same kitchen, next to the hot cup of coffee, a little bit further down on the counter, you place a glass of ice water or cold, lemonade and leave overnight. When you come back, that lemonade is no longer cold, right? It's room temperature because heat transferred from the kitchen to the colder bottle of lemonade. Again, heat spontaneously transfers from hot to cold, never the other way around. You have never left a lukewarm cup of coffee on the counter, come back a day later, and it's boiling hot. Right? That has never happened and never can happen. Heat does not transfer from low temperature to high temperature, it transfers from high to low. Now, there are ways we can trick heat into transferring effectively from low to high by using heat pumps and things like that, like refrigerators, air conditioning units. But we'll talk about those. Those are specific examples that do not violate this principle. In both cases of refrigerators and air conditioners, heat still transfers from hot to cold. Heat is not the same as thermal energy. Thermal energy is the amount of energy, the kinetic energy of the molecules in an object. So let's imagine a ball of a certain temperature. All the little molecules in that ball are moving about, vibrating at a certain average speed, giving that ball some thermal energy. Or a tub full of water. All the water molecules are moving about at some speed, giving the amount of water some thermal energy. Heat is the transfer of energy. Thermal energy is the amount of energy that's in the kinetic energy of the objects, right? So thermal energy, think of it like a bank account. Like there are many different places you can put your energy money. You can put your energy money in the kinetic energy of an object, the gravitational potential energy of an object, the elastic potential energy of an object, the thermal energy of an object. Heat is a transfer, right? Is a transfer of energy from one object to another. So it's not a bank account, it's a deposit, if you will. Heat has units of joules. Heat transfers energy, right? It usually transfers it to the thermal energy of an object or from the thermal energy of an object, but it is not the same as the thermal energy of an object. Heat has units of joules. What else has units of joules? Well, energy, but work also has units of joules. And work can also change the thermal energy of an object. It doesn't have to just be heat. For instance, my hands, my palm of my hands are at some temperature. There's some thermal energy there. Now I can set them on a hot stove, I don't recommend doing that, or put them in hot water, and heat will transfer energy from the warmer water to my cooler hand, warming my hand up, increasing the thermal energy of the palm of my hand, or I can increase the thermal energy of the palm of my hand doing work, right? I just did a lot of work. That frictional force caused the palms of my hands to heat up. So heat has units of joules. Now heat, again, transfers energy from one system to another. So here we have the environment. T sub E is the temperature of the environment. Here we have the system, and the example I used, the hot coffee mug. T sub S is the temperature of the system. If T sub S is greater than T sub E, in that the coffee mug is hotter than the environment, then the transfer is negative. You get negative heat on that coffee mug, effectively cooling off or reducing. Negative heat, think of it as a negative debt on your thermal energy account, right? You lose thermal energy. If the temperatures are the same, there's no heat transfer. Technically, there kind of still is. The coffee mug is still trying to heat its surroundings, and the surroundings are still trying to heat the coffee mug, but those energy transfers balance. So we just say that the heat is zero. So if you bring in a bottle, a bathtub toy for your children are taking a bath, or when you were younger, you were taking a bath, and the water was, say 90 degrees, and then someone puts in a toy that's 90 degrees, that toy isn't going to change temperature, and neither will the bath water. And then finally, if the system is at a lower temperature than the environment, the cold glass of lemonade on the counter in your kitchen, for example, then the heat transfer to the system is positive. Your cold glass of lemonade, whatever its thermal energy, will increase as heat is transferred from the environment to the cold glass of lemonade. Now, interesting thing, humans are terrible at actually measuring absolute temperature, but we're wonderful at measuring how much heat is taken from us. So when you feel something and it feels hot or it feels cold, we're not actually measuring the temperature of that object, at least not directly. We're measuring how quickly heat is either taken in by our skin or lost by our skin. That is heat. So for example, a little experiment you can do with kids, especially, it's fun. 3 tubs of water. Ice water or cold water in one. Warm water, but still able, like bath water, warm bath water in another. And in the middle, room temperature water, tepid water. Have you stick the hand in the ice water. Again, for kids, maybe they won't want ice water, just cold water. Bath water for the other hand, and let them sit there for about a minute. Then both hands come out and both go in the tepid water. The hand that was in the cold water will think the tepid water is warm. The hand that was in the warm water will think the tepid water is cool, because our skin is measuring temperature differences. A wonderful example of this is sheets in the winter, right? Cotton or silk sheets feel cooler on our skin than flannel does. Even though the sheets are on the same bed in the same room, kept at the same temperature. So if you actually measure the temperature of your bedroom sheets, if you had 3 beds, cotton, silk, and flannel, all 3 sheets are at the same temperature. However, when you climb in, one feels cooler than the other, right? Silk would feel cooler than flannel. The reason for that is silk is better at pulling heat from our bodies than flannel is. Flannel is insulating. And we'll talk a bit more about energy transfer mechanisms in a little bit later today, or a little bit later in this set of videos.